Okay, I wanted to record a video showing us how to draw different covalent molecules. So first of all, if you have not already filled out these notes on how to draw covalent compounds, these are found in the Canvas folder called Coulson Completed Notes. So go ahead and fill out all of the covalent notes up until this point, and then I will walk you through the different examples and how to do those. And it would also be helpful for you to have your periodic table. So starting with the first example of silicon bonded to 4 fluorine atoms, if we're looking at these two atoms, I have silicon right here and fluorine right here. My first step is to add up the total number of valence electrons available for bonding in the molecule. So silicon has 4 valence electrons, I'm going to write that down, and fluorine has 7 valence electrons, so I'm going to add to that my 7 valence electrons, but because there are 4 of them, I have to add that 7 4 different times, or you can just add 4 plus 28. And so I'm left with 32 total electrons. So now I've done step 1, and my second step is to determine the central atom. So the central atom will have the most bonds and is usually the leftmost, or whatever is furthest to the left on the periodic table, except we have 2 rules that we always have to follow. One is that carbon is always the central atom if it is part of your compound, but in this case carbon is not part of our compound, so that does not apply. And then the second rule is that hydrogen is always the opposite. It's always a terminal atom or an outer atom because it can never go in the center, and we'll talk about that a little bit later. Your third step is to symmetrically arrange all the other atoms, so your terminal atoms, outside or around the central atom by place a single bond between each one of them. So let's look at this. The one that is furthest to the left on the periodic table would be silicon, so that's going to be my central atom. I'm going to zoom in so I have more space to draw it. So I have silicon is going to go right in the middle. My second step is to, or the third step on the paper, symmetrically arrange my fluorines around my silicon. And then I'm going to draw a single bond connecting them together. So each one has to be bonded to your central atom. And that bond, if you took the other notes, you would see that the bond, that's represented by a line, represents a shared pair of electrons. That is what a covalent bond is. So each line represents 2 electrons that I used. This number 32 comes from the number of valence electrons, like we said. We added them up, and we have to use all of them. And we can use no more, no less. We have to use exactly 32 electrons in this case. So we're going to keep track as we go through. So we have 2, 4, 6, 8 total electrons that we used for bonding, so for single bonds. So 8 electrons for single bonds. So this is written, I think, on the notes that I posted to Canvas, but that way you can follow along and kind of understand what this means out to the side. So then my fourth step is, so as already says, subtract the number of electrons. We already did that part. Place remaining electrons around the outer atoms, so your terminal atoms, anything that's not your central atom, to reach octet. So you're also going to subtract that total from your number of electrons used. So if I'm here, I have a total of 24 electrons remaining in my bank, if we want to call it that. I'm going to put those around my terminal atoms until each of my terminal atoms has an octet. And so what that normally looks like is they will look like they have 6 electrons on them because they have 3 lone pairs, but that shared pair still accounts for 2 electrons that are part of that atom's valence shell and still part of that atom's valence shell. So that's what we mean by a shared pair. This pair of electrons belongs to both silicon and to this fluorine. Similarly, this one belongs to both that silicon and that fluorine, or silicon. So we have 1, 2, 3, 4, 5, 6, 7, 8 electrons for that fluorine, so now that fluorine is stable. And that used 6 electrons that we hadn't already accounted for because, again, that bond right there was accounted for right there. So we have 18 electrons left over to put on the rest of these. And so you'll see that the math works out really nicely for us here. We have 6 on that one, 1, 2, 3, 4, 5, 6 on that one, 1, 2, 3, 4, 5, 6 on that one. So you can just go ahead and subtract all 18 here, and I have nothing left over. So in this case, it worked out perfectly. This one ends up stable, this one is stable, this one is stable. And it says if any electrons remain, place them on the central atom. But like we said, we have nothing remaining. We have 0 left over. And then the last part, if the central atom is not stable, use double or triple bonds until it becomes stable. So it is not until this point, when all electrons have already placed all electrons. So you will not start doing double and triple bonds until you've already placed all of the electrons that you have available to you. And then the last step is always double check that all atoms are stable at the end and that you used exactly the right number of electrons. So if I go over here, again, the math on this one worked out beautifully, where I had 32 electrons to use. I used 8 for my bonds. I used 6 on each of my fluorines, and when I subtracted, I ended up with 0. Silicon in my center has 2, 4, 6, 8 total electrons around it, so it is also stable. I don't need any double bonds. I don't need any triple bonds. And then if you wanted to double check at the very end, I think that the check marks are a good way to kind of keep track of who is stable and who is not yet, or you could do a little smiley face like we did with ionic bonding. But the most important thing is that you go back and you double check that yes, they're stable and I used the correct amount of electrons. So I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32 electrons used. So that's it for this one. Moving on to my next one, since these are kind of close, I'm going to change my color. If I do carbon dioxide, oops, I'm drawing all over the place here. I thought I could zoom still. My bad. Okay, so carbon dioxide, again, we're following the same rules. So if I look at this one, first step is to add up the total valence electrons from both. So carbon dioxide has, dang it, drawing, not with touch. Okay, so carbon and oxygen bonded together. So carbon, of course, is further left, and carbon is, again, the rule that says it has to be always the central atom if it's part of my compound. This one has 4 valence electrons, so we're going to use that, and then this one has 6 valence electrons. Sorry about the random markings, we'll erase that. So carbon dioxide, we have carbon with 4, plus oxygen with 6, plus a second oxygen with 6, so we have 4 plus 6 plus 6 equals 16 electrons to work with. And then again, like I said, my central atom is going to be carbon, because carbon is always the central atom if it is available. And then I symmetrically arrange my other atoms, my terminal atoms, around my central atom. So any other elements that are not your central atom are considered what we call terminal atoms, or outer atoms. So I would put oxygen right here and another oxygen right there. And so as it stands, we just have oxygen floating next to a carbon and floating next to another oxygen. They're not in a compound right now. They are not in a compound until you add bonds to them. And every single time we're going to start with single bonds. So I do a single bond here and a single bond there. Again, those electrons, or those lines, represent 2 electrons each. So that's 2, 4 electrons. So 16 minus 4 from my single bonds. And then my next step, if you get confused, you should have this to reference, like on your notes it's right above it, so it's super simple. Symmetrically arrange it, done, subtract the number, done. Place remaining electrons around the outer atoms to reach the octet. So I'm going to take my 12 electrons that I have left over and put them on my outer atoms. 1, 2, 3, 4, 5, 6. And now my oxygen is stable because it has 2, 4, 6, 8 electrons. Then I've got 2, 1, 2, 3, 4, 5, 6. And then that one is stable as well. So I used all 12 of those electrons, and there are none left over. So if I look at that, now it says if any electrons remain, place them on the central atom, but none remained. So if the central atom is not stable, use double or triple bonds until it becomes stable. So if I come back here, my central atom is not stable because all it has is 1, 2 bonds on it, and so that's a total of 4 electrons, and it needs 8 in order to be stable. So here's where we're going to start sharing electrons, or pushing lone pairs. These lone pairs of electrons are unshared pairs. Push that towards the single bond, and it's going to become a double bond there. So at that point, these electrons, you can erase them if you want to, or you can draw an X through it. So normally if we have these on paper and I'm using a pen or something, I'll just draw an X to show very clearly that they are no longer there. Otherwise, you just need to erase all of that, and you end up with a double bond here. And because it takes less energy to form two double bonds than it does to form a triple bond, it's going to do the same thing on this side and keep things symmetrical. So it does end up being a symmetrical molecule, this one, but it's not because being symmetrical is one of the rules, it's because it takes less energy to form two double bonds. So I'm going to take this pair of electrons. It's a lone pair currently because it only belongs to oxygen, it's not being shared, but then I move it over here and now it becomes a shared pair and it's a part of both oxygen and carbon's valence shells. So then this goes away, so you can either erase that or you can just show that it's gone with an X, and then you're left with two lone pairs on this oxygen molecule, or on that oxygen atom, two lone pairs on that oxygen atom, and then a double bond here and a double bond there. And so now my oxygen is still stable. It has 2, 4, 6, 8 electrons still, so that still applies. This one still has 2, 4, 6, 8 electrons. And now my carbon in the center has 2, 4, 6, 8 total electrons. The other thing that's important to do, especially once you start moving things around and erasing and rearranging, you need to go back to your original number of electrons and make sure that you didn't accidentally forget some or put in too many. So if I have 16 total electrons to use, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I used the correct number of electrons. So this is our final shape for carbon dioxide. The third, I'm going to do a different color again. Let's use pink. Oops, keep doing this, the draw with touch. Okay. The third molecule that we will draw is carbon monoxide, so we're following the same rules. We already found where carbon and oxygen are. They have the same number of valence electrons as before, but now instead of having two oxygens, we just have one. Okay, sorry. Then go in here. I have 4 valence electrons from carbon plus 6 valence electrons from oxygen. That equals 10 total electrons to work with. My central atom is still carbon. And then I'll put in quotes, symmetrically arrange my oxygen around the carbon, but since there's just one of them, it really does not matter where you put it. So just to mix things up, I'm going to put it over here, but normal people put it over there. Then, just like before, you have to tie that outside atom to your central atom with a single bond. So I'm going to draw a single bond. And that single bond represents 2 electrons. So I'm going to subtract that from my total. I have 8 electrons left over. Then with those 8 electrons, I first put them on my terminal atoms. So in this case, that's my oxygen. I'm going to draw a better oxygen. So I have 1, 2, 3, 4, 5, 6 electrons on oxygen. So I used 6 of them. So I like this example because it doesn't end up with a neat, pretty little number like all the other ones did. So this one, I have 2 electrons left over. And so if you get lost, again, your first line of defense is go to the instructions, follow these step by step. I added my valence electrons, I did my central atom, I symmetrically arranged them, I subtracted, I placed them around the outer atoms. Good. Okay, now here it tells you exactly what to do. If any electrons remain, place them on the central atom. So it is allowed to have lone pairs on your central atom. In fact, if you look at the next page, there's a specific column that we talk about that in. So I'm going to put a lone pair of my 2 remaining electrons. Now I used those 2, and I have 0 left over. Sometimes it will be more than that, and you'll just continue to put them on your central atom. And if central atom is not stable, use double or triple bonds until it becomes stable. And again, always double check at the end. So if I go back to my picture, I have 1, 2, 3, 4, 5, 6, 7, 8 electrons on my oxygen. So oxygen is stable. My carbon is not stable because I have 1, 2, 3, 4 electrons. So I need to take these 2 electrons. I'm just going to erase them and turn that into a double bond. That still helps out my oxygen, so my oxygen is still stable. I can keep that check mark there, but my carbon is still not stable. I just have 2, 4, 6 now, so I'm going to take another pair of electrons and turn it into a shared pair. So we need to be careful about the terminology that we use there. It's not donating its electrons, it's not giving its electrons to carbon. Oxygen in this case is sharing its electrons with carbon because it's a covalent bond. They still belong to oxygen, it's just that carbon is using them too. So those those electrons can act as part of the valence shell for both of those atoms. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons that I used, and each of them are stable, 2, 4, 6, 8, and then 2, 4, 6, 8. So I would have oxygen triple bonded to carbon with a lone pair on each one. And then I think this next one will probably be the last one I do on this video. If you like it enough and you reach out and want me to explain more, I can do more videos like this. But I feel like at this point you're probably starting to get the picture, and if you need additional help, you can always come to tutorials. Okay, oops. So if I do NH4 with a +1 charge, I find nitrogen over here, and hydrogen is my non-metal that's over on this side. So remember, even though it's on the positive side, it is a non-metal, so it participates in covalent bonds. Hydrogen, even though, again, it's leftmost on the periodic table, that's what we're trying to follow, hydrogen is one of our exceptions, that it's always a terminal atom, so it will never be your central atom. So in this case, nitrogen with its 5 valence electrons will be my central atom, and hydrogen contributes 1 valence electron. So I have 5 plus, and then 4 electrons from hydrogen because it's 1 plus 1 plus 1 plus 1, and that gives me 9 electrons. But then I have this little +1, and you have to remember that +1 means that this whole thing has, I'm going to say that thing has lost 1 electron because it has an overall +1 charge. That means it has 1 less negative thing acting on it. So instead of 9 electrons, this actually has only 8 electrons to work with. So I'm still going to draw it the exact same way, but now instead of 9 being my target number, it's going to be 8. So I'm going to put my nitrogen in the center, symmetrically arrange my hydrogens around the nitrogen, draw my single bonds, 2, 4, 6, 8, so -8, and that equals 0. And then I have nothing left over, nothing to put on my central atom. Double check everyone is stable. Hydrogen is stable with just 1 bond because these 2 electrons count towards hydrogen's valence shell, and hydrogen only needs 2 to be stable, but nitrogen needs 8, so 2, 4, 6, 8. Everyone is good. Alright, actually I changed my mind. I do want to do this one too. I'll leave water for y'all to do by yourself. But C2H2, I get a lot of questions about this one. This question is on here so that you can see what a carbon chain or like a little baby carbon chain looks like. That's more like organic chemistry. We don't really do that, but just in case, oops. So C2H2, we do it the exact same way. So carbon has 4 valence electrons, but there are 2 of them, so I'm going to add a second one. And hydrogen has 1 valence electron, but there are 2 of them, so I add 1 plus 1. 4 plus 4 plus 1 plus 1 equals 10 electrons to work with. My central atom is always carbon if carbon is part of my molecule, but here I have 2 carbons, so I'm just going to put them both into the center. So carbon and carbon. You need to draw them separately. You can't just do like C2 in your center. It has to be 2 separate atoms. And then I'm going to symmetrically arrange my hydrogens on the outside of my carbons. And then right now I just have an atom next to an atom next to an atom next to an atom. If I want it to be part of this compound, I have to bond them together first. So single bonds always to start. You will never start a compound with multiple bonds. So then I drew 2, 4, 6 electrons. So I have 4 left over. So if I'm looking at this, my hydrogen is stable because it has a bond, and that's 2 electrons, and that's good enough for hydrogen. This one is also stable. Also notice I did put a bond between my 2 carbons because again they have to be bonded together somehow. So then my 4 electrons, I personally would put them like this so that I have 1, 2, 3, 4, 5, 6, 7, 8 electrons on that carbon, but it truly does not matter where you start them. You're going to end up with the same answer no matter what you do. Some people prefer to keep it symmetrical, 1, 2, 3, 4. And then either way, you used all 4 of those electrons, and now there's nothing left. So now we're at the point where we're looking at this, and we're like, okay, I've used all 10 of my electrons, my hydrogen is stable, that hydrogen is stable, and my carbons are not stable. So they are going to share these electrons. So now instead of a single electron or a lone pair or however you decided to draw it, this is going to be a shared pair of electrons between the 2. And so just like we did on the previous page with our diatomic molecules, we're going to draw these together. Carbon's not diatomic, so don't confuse that. But similar to when we drew like fluorine, 1, 2, 3, 4, 5, 6, 7, and then fluorine 1, 2, 3, 4, 5, 6, 7. When we had these and we circled them and then that turned into the line, that's the same thing that we're doing here. So we do fluorine, single bond into fluorine, and then your electrons all around the outside of it. So that's what we're going to turn this into so that our picture looks a little bit more like the other ones that we were doing. So we have hydrogen single bonded to carbon, so that's what we're looking at here, hydrogen single bonded to carbon, and then carbon has a single bond to the other carbon, and then this will turn into another bond and another bond. So that's going to be a triple bond between your two carbons, 1, 2, 3, and then my carbon, and then I still have a single bond to the hydrogen. So if I'm looking at this, again, my hydrogen is stable because it has one bond. This carbon is stable because it has 2, 4, 6, 8 electrons. This carbon is stable because it has 2, 4, 6, 8 electrons. And this hydrogen is stable because it has its one bond. So everyone is happy, everyone is stable. And then again, at the end, go back and double check, did you use the amount of electrons that you were supposed to? So this is 2, 4, 6, 8, 10 total electrons. I did. So you are able to draw all sorts of different covalent compounds. Hopefully this video helped. Give me feedback if you'd like to. And like I said, I'll leave H2O for you to draw on your own, or you can look at the notes for that one.